March 23, 2021. A 400-meter container ship named Ever Given simply stopped. For 6 straight days, the Suez Canal, the shortest sea route between Europe and Asia, was completely blocked. Global supply chains froze. The physics that caused it was brutally simple. Visual. Cut to clean 3D animation of the Suez Canal cross-section. Show water flow lines compressing under the hull. When any ship moves through a narrow channel, it displaces its own weight in water. In open ocean, that water flows away freely. But in Suez, a man-made ditch only 200 to 300 meters wide and barely 24 meters deep at the edges. The water has nowhere to escape. Pressure drops under the keel. The ship sinks lower. This is called squat effect. At the same time, water squeeze between the hull and the sloping sand bank creates unequal forces, pushing the bow away while sucking the stern toward the wall. That's bank effect. The longer and heavier the ship, the worse both effects become. The Ever Given proved the models correct in the most expensive way possible. Visual. Split-screen CFD simulation. Red high-velocity zones. Ship outline yawing dangerously. Simple equation overlay. Delta P equals 1/2 rho V superscript 2. Now imagine trying to push something even bigger through the exact same ditch. Visual. Dramatic cut to USS Gerald R, Ford, CVN-78. Massive overhead shot. 337 meters long, 78-meter flight deck, 100,000 tons. Slow zoom on the hull entering the canal on March 5, 2026. On March 5, 2026, the world's most advanced nuclear supercarrier, USS Gerald R. Ford, entered the Suez Canal with its full strike group escort. On paper, this should have been impossible. A ship longer than the Empire State Building is tall, wider than most city streets, and heavier than 70 fully loaded 747 jumbo jets, sliding through a canal that once stopped the entire planet for a week. So how did engineers beat the same fluid dynamics nightmare that humbled global trade? That's what we're breaking down today, from first principles. Visual, title card slams in TEHRAN Shaken, how the USS Gerald R. Ford defeated the Suez Canal. Music swell transition to main script. In March 2021, a single 400-meter container ship named Ever Given got stuck in the Suez Canal. For 6 days, the world's busiest trade artery was completely blocked. The physics that cause it? Simple. When a massive hull moves through shallow, narrow water, the laws of fluid dynamics take over. Water has nowhere to go, pressure drops under the keel, and the ship literally sinks lower while its stern gets sucked toward the bank. On March 5, 2026, the same canal watched something even bigger slide through without incident. The USS Gerald R. Ford CVN-78, America's newest 100,000-ton nuclear supercarrier, accompanied by the destroyer Bainbridge. On paper, this should have been impossible. So how did civil infrastructure and naval engineering beat the same physics that stopped global trade for a week? Let's break it down from first principles. Animated world map. Red line shows Mediterranean to Red Sea route via Suez. 7,000 nautical miles saved versus Cape of Good Hope. Overlay carrier flight range circles from Red Sea versus Mediterranean. Cut to satellite view of Suez Canal today with ship traffic density. Aircraft carriers exist for one reason: to project air power anywhere on Earth faster than any other platform. In a crisis, the shortest path from the U.S. East Coast to the Middle East is through the Suez Canal. Going the long way around Africa adds 2 weeks and thousands of tons of fuel. But Suez is not an ocean. It is a 193 km long man-made ditch, dug through desert sand with strict geometric limits. That's the civil infrastructure problem. How you design a waterway that can swallow the largest warships ever built while still functioning as a 24/7 global logistics highway. When a ship moves, it displaces its own weight in water. In open ocean, that water flows freely under and around the hull. In a canal, only 200 to 300 meters wide and 24 meters deep at the edges, the water is trapped. Result? Squat effect, dynamic increase in draft. The faster the ship moves, the lower the pressure under the keel, the deeper the ship sits. For a 337-meter vessel, squat can add 1 to 1.5 meters to the draft. Ford's static draft is already 12 meters. Get it wrong, and you kiss the bottom. Bank effect, asymmetric pressure. Water squeeze between hull and sloping sandbank creates higher pressure on one side, sucking the stern toward the wall while the bow is pushed away. The longer the ship, the bigger the yaw moment. Split-screen CFD animation. Water velocity vectors turning red near banks. Ship outline yawing. Overlay simple vector diagram. Delta P equals 1/2 rho V superscript 2. Why does this happen at the molecular level? Water molecules cannot compress, so the only escape is forward or backward, in a confined channel that creates a Venturi-like acceleration under the hull and lateral forces that no rudder can instantly overcome. For 50 years, engineers have known this. The Ever Given proved the models were right. So how does a 100,000-ton, 256-foot-wide flight deck monster, literally at the 77.5-meter beam limit, not repeat that disaster? Exploded 3D model of Ford hull plus canal widening timeline, 1975, 2010 today. Then live action stills from the March 5th, 2026 transit. Tugs fore and aft, small craft security teams on catwalks. 2 parallel engineering loops close the gap. First, the canal itself. Egypt spent billions widening and deepening it. Today, the minimum cross-sectional area is 4,800 square meters. Maximum authorized draft is 66 feet, 20.1 meters. Ford's 39-foot draft leaves a huge safety margin. The banks were reprofiled with gentler slopes to reduce bank effect forces. New bypasses and wider passing sections let convoys keep moving. Second, the ship. Ford's waterline beam is only 41 meters. The famous 78-meter flight deck overhangs high above the water and cleared canal banks. For massive controllable pitch propellers driven by 2A1B nuclear reactors give instant torque at low speeds without worrying about fuel burn. The reactors deliver roughly 700 megawatts thermal each, enough combined electrical output to power a city of 100,000 homes. But here that power keeps the ship precisely on the centerline, even at 6 to 8 knots transit speed. Add professional Suez pilots who have done this thousands of times, plus a pair of tugs with the tightest bends, and the impossible becomes routine. Ship speed versus squat depth for different canal widths. Ford plotted safely inside the green zone. Side-by-side cost comparison graphic. For construction, $13 billion versus Suez widening phases in billions. Then risk heat map. Wind, current, human error. Bigger is never free. The Ford size gives it 90-plus aircraft and unmatched sortie rates, but operates at the absolute physical limit of Suez beam clearance. One strong crosswind, and the bank effect yaw moment spikes. The Canal Authority still closes the waterway for large vessels during sandstorms. Nuclear power means unlimited range, but the reactors and shielding add hundreds of millions in upfront cost and require a 50-year refueling cycle that ties the ship to specialized yards. The canal itself? Every widening project costs Egypt hundreds of millions and still leaves the entire global economy vulnerable to one grounding. That's the civil infrastructure reality. You can push the physics envelope, but you never erase it. Final split screen. Ford and open Red Sea launching aircraft versus static canal cross-section diagram. Fade to human scale. One engineer standing on the flight deck. Is this technology viable for future? Yes, barely. The Ford class and the expanded Suez Canal are a perfect example of civil infrastructure and naval engineering dancing right on the edge of what fluid dynamics will allow. On the edge of what fluid dynamics will allow. Economically, a Suez transit for a ship this size costs roughly $1 million in fees. The carrier itself costs $13 billion to build, but the alternative, sailing around Africa, burns millions more in fuel and time. In geopolitics, time is the ultimate currency. Final thought. We keep building bigger machines and wider ditches because human ambition refuses to accept the limits nature wrote into the water. But every transit is a quiet reminder. The laws of physics don't negotiate. They only allow careful, expensive compromise. And on March 5th, 2026, that compromise held. Engineering isn't about breaking limits. It's about understanding them. Subscribe/next video tease.